All right, today we're going to dive into a new physics paper that, well, it connects two things you would literally never think to put in the same sentence. A spinning bucket of water and a single particle of light. Yeah, you heard that right. Let's get into it.
I know, it sounds like the setup for a really weird physics joke, doesn't it? But believe it or not, the answer is tucked away inside the math, and it reveals this kind of secret, shared language that connects the everyday world of fluids with the super weird quantum world of light. So, let's start by unpacking the mystery of the bucket. So our journey doesn't start in some giant billion-dollar particle accelerator. No, we're starting with something way simpler. We're in a lab with just a cylinder of water that's spinning.
So, picture this. You've got a cylinder of water, and it's spinning around at a nice constant speed. Then, from the bottom, something gives it a quick little push upwards. Now, your first thought is probably, okay, I'm going to see a ripple on the surface, like right away. But that's not what happens. Not even close. Instead of an instant splash, there's this pause, a really noticeable delay. And when the signal does finally show up at the top, it's this weird push-pull thing. If you push up from the bottom, you get a little dip on the surface. If you pull down, you get a little rise. So what in the world is going on here? Why the wait?
Well, the answer is a very special kind of wave. And this wave is kind of the hero of our story, but it has one rule. It only shows up if the fluid is spinning. It's called an inertial wave. See, in a regular bucket that's just sitting there, a push from the bottom would pretty much travel straight up. But the second you add rotation, everything changes. The energy is forced to travel along these weird slanted paths. It's like it's taking the scenic route to get to the top.
And this is where the paper gives us this absolutely perfect analogy to help us visualize it. Imagine a row of dominoes, but they're not standing straight up and down. They're slanted. If you tip over the one at the very bottom, that tipping has to travel all the way up the slanted line before the final domino at the top falls over. That delay, that's exactly what's happening with the energy in the water.
And get this isn't just some hand-wavy idea. The physics behind this is super precise. For their specific lab setup, we're talking a cylinder 30 centimeters deep, spinning at a certain speed. The theory predicts the wave will hit the surface in 4.1 seconds. Bam! A specific, testable number.
Okay, so we've got a delayed wave. Makes sense. But that's only part of what's going on inside this bucket. Because that little push at the bottom, it doesn't just send a message up. It also creates a twist in the water.
So how does this swirl even happen? Well, that initial push displaces the water, right? It moves it. And because the whole thing is already spinning, that little bit of displacement creates these teeny tiny vertical whirlpools. Physicists have a name for this, vorticity. And when all those little whirlpools team up, they create a bigger circular flow, what the paper just calls swirl. So it's like a chain reaction. A push creates vorticity, and vorticity creates the swirl. And here's where it gets really cool. The direction of that swirl totally depends on the direction of the first push. If you push up, you get a swirl that spins with the bucket's rotation down below, but against it up top. And if you push down, you get the exact opposite. It's this perfectly symmetrical little dance. And that brings us to this key idea the paper calls reversible swirl. Because if you give the water a perfectly balanced push, then pull, the with rotation swirl and the against rotation swirl basically just cancel each other out. The water pretty much goes right back to how it was, with no extra spin left over. It's like a twist that perfectly untwists itself. Remember that.
Okay, hang on to that idea of a twist that untwists, because we're about to make a jump, a huge jump. We're leaving the bucket of water behind and heading into the world of a single particle of light. I know, it sounds totally random, but you're about to see that they're speaking the exact same language, mathematically at least.
And this right here is the heart of the whole paper. It's this direct connection between those knots of spin, that vorticity we just saw in the water, and similar kinds of knots that scientists can actually create in a beam of light.
So, in the crazy world of modern optics, physicists can now play with individual photons, twisting them into these super complex patterns. A good way to think about it is like they're tying intricate knots in a property of the light, like its polarization. It's like tying a knot in a ribbon that you can't even see. These amazing little structures, they're called optical skyrmions.
And here it is. This is the big reveal. On the left, that's the math physicists use to count the twists in one of those light knots, an optical skyrmion. And on the right, that's the math for the vorticity, the twists in our bucket of water. Just look at them. Forget the symbols for a second and just look at the structure. They're identical. It's the same exact blueprint for two things that couldn't seem more different.
So what are these twin equations actually doing? Well, they're calculating something called topological charge. Now that sounds super complicated, but the idea is actually pretty simple. It's just a number that counts how many times a field, like the polarization of light or the spin of the water, how many times it wraps or twists around itself. The answer is always a whole number, like +1, -2, or 0.
And once again, the paper comes through with a great analogy. Figuring out the topological charge is basically just like counting how many times you've twisted a shoelace around itself. That's it. It's just a really solid way to measure the knottedness of something, and it doesn't matter if that something is a bucket of water or a single photon.
Okay, so water and light share the same math. The big question is, so what? Why does this formal correspondence, as the paper puts it, actually matter?
So let's just pull this all together. We started with a simple push in a spinning bucket, which created a wave that was predictably late to the party. We saw how that wave makes a reversible swirl that can untwist itself. And then the big one. The math that describes those twists in the water is identical to the math for knots in a photon. What this tells us is that there might be this shared hidden language connecting the classical world of fluids and the quantum world of light. And that opens up some really cool new ideas. Like, could you use a fluid system as a blueprint for creating new kinds of exotic structured light?
I mean, this entire journey started with a spinning bucket of water, and it ended with a quantum particle of light. It really makes you wonder, right? What other absolutely profound secrets are hiding out there in plain sight, in things we see every day, just waiting for someone to find the right connection, the right analogy, to unlock them?